Good morning, everyone. Today I'm going to share some recent progress about estimating stochastic closures using sparsity promoting ensemble Kalman inversion. So the general motivation of this work is to predict climate change, which involves phenomena at a wide range of scales. And considering the fact that we need to simulate the global Earth system for decades in order to predict climate change, it is almost impossible to resolve all these phenomena. And that's why closure models are needed for unresolved processes, such as microphysics, turbulence, and part of cloud dynamics. And to briefly introduce the closure problem, let's imagine that we have a dynamical system in general form as presented at right side, where we cannot afford to resolve every details of the state vector small u. And the common practice is to introduce some kind of filters, either spatial or temporal, and then we can get a filter state capital U. An example related to the illustration figure here is that the filter state U is grid average of the original state small u. And with that, we can derive a Kalman equation for the filter state capital U as well. But in many applications, just because the original dynamics F is nonlinear and the dynamics of the filter state F bar often depends on unresolved scale small u as well. So in order to simulate the Kalman equation for filter state, we still need to construct an F tilde that only depends on the filter state capital U, and hope that F tilde can approximate the true dynamics of the filter state capital U, the F bar here. However, this assumption only holds very nicely if we are dealing with a system with clear scale separation. For example, heat transfer at macro scale and molecular dynamics at micro scale. But in many applications, there is no clear scale separation, which means that F tilde in many cases is not sufficient to approximate F bar. Therefore, in this work, we propose to model the difference between F bar and F tilde by a deterministic term M and also a stochastic term. So here, W dot represents the Wiener process. And there are different technical tools that we can use to further parameterize the unknown term M and also the diffusion coefficient sigma, such as dictionary learning, reproducing kernel Hilbert space, and also neural networks. So after choosing a specific tool that represents these two unknown terms, we are left with unknown parameters alpha and gamma. And here we denote them together as unknown parameters theta. And in this work, we want to estimate the unknown parameters theta from some data y using ensemble Kalman inversion. So here I will briefly introduce the ensemble Kalman inversion EKI we use in this work. So the general inverse problem we want to solve has the form presented at top, where theta represents unknown parameters. G is some kind of forward map that bring unknown parameters to data space. And eta here represents the noise associated with how we generate data y. And in the middle, I show the EKI updating formula. So the J here is the index of ensemble, and M is index of EKI step. So the updating formula here can be understood intuitively in such a way that we first calculate the mismatch of G theta and the data y, and we normalize the mismatch in data space. So here C is the covariance within data space. And we normalize the mismatch in data space first, and we then project this normalized mismatch to parameter space, and we use that projected mismatch to update the estimation of unknown parameter theta at m EKI step. And then we do it iteratively until convergence is achieved. So there are several advantages of EKI. First, as we notice here in the updating formula, it does not require gradient information for map G, which makes it a derivative-free optimization scheme. Also, it is robust to noisy evaluations of the forward map G because it's an ensemble-based method. And the core task is equivalent to a convex optimization problem. So I will revisit this point at later of this talk. Before that, let's see some results about learning stochastic closures. So the first case we studied is noisy Lorentz 63 system. For the true system, it's just the standard Lorentz 63 system plus a noise term. And for the model system, we assume that we don't know about the diffusion coefficient sigma here, and also we don't know the linear term of the dynamics of state variable x2. And we want to learn both terms by using the data of first and second moments of all the state variables. So here I present the comparison of moments between the true system and model system. The red bars are results of true system and the blue bars are results of model system. And as we can see here, both cases provide us relatively good agreement with true system in data space for first and second moments. And then we ask ourselves a question, does it mean the two models are equally good? So to answer this question, we try to integrate the system for a much longer time and plot the invariant measures here. So for those who are not familiar with the terminology here, you can just think it's the probability density of each state variable for a very long time trajectory. And as we can see here, when we look at the invariant measures, we can see that the model system with stochastic term has much better agreement with the true system, demonstrating the better generalization capability if we include the stochastic term into the learning process. So the second example we studied is the reduced Lorentz 63 system. So this is a system was studied by Professor Tim Palmer in about 2 decades before. And first, we transformed the standard Lorentz 63 system into new coordinates, where the third dimension carry list of the energy of the system. And if I remember correctly, it only carries about 5% of the total energy of the whole system. And then a straightforward way to build a reduced order model is just to neglect the third dimension, which provide us the reduced order model as shown at the bottom. And in the original work, it showed that by doing so, the reduced order model lost all the chaotic behavior of the true system. But more interestingly, if we try to add some even very simple stochastic term, just constant white noise, the modeled system can at least get the chaotic behavior qualitatively correct. So inspired by these results, we try to use our framework, try to learn stochastic closures for the reduced order model by adding deterministic term and the stochastic term and try to learn M1, sigma 1, M2, and sigma 2. And here I show the results of invariant measures for state variable A1 and A2 comparing to the true system. As we can see here, if we try to learn a more sophisticated stochastic closure by using our framework, we can achieve quantitatively agreement with the true system in terms of the invariant measure, the probability density of each state variable for a longer time. So for the second part of my talk, I will introduce the sparsity promoting ensemble Kalman inversion and some results associated with that. So as I mentioned before, the core task of EKI, the ensemble Kalman inversion, is equivalent to a convex optimization problem. To further show this point, let's introduce a new variable, W equals to G theta, and then we can get an augmented state V as theta and W. And with that, we also get an augmented noisy observed dynamical system as presented in the middle. And if we try to apply kind of filter upon this system, it's actually equivalent to solving the optimization problem as shown at the bottom, whose loss function J try to minimize the difference between data and the H-way, and also try to minimize the difference between V and the perceived V. So you can think this is the contribution from data and this contribution from the model prediction at a certain step. And the optimization problem tried to find the minimizer of this loss function. And as we can see here, a very good property is that the loss function is actually quadratic with respect to unknown V, the augmented state here. And if we rearrange a little bit, we can get a very nice standard form of quadratic programming in terms of V. And imposing sparsity within EKI is just try to impose the constraint upon the L1 norm of the augmented state V once we project it to the parameter theta. But as we notice here, the constraint here is not linear. So there is still some work we need to do before we can solve it with standard algorithm. So for that part, we follow the technique suggested by Professor Topshiali in his Lasso paper. So we try to introduce two variables, V plus and V minus, and we use this variable transformation to get a kind of augmented optimization problem where the loss function itself is still quadratic, but the constraint here is just linear inequality constraint. So we can solve this problem directly with standard quadratic programming algorithms. So, and then we tried to study the noisy Lorentz 63 system by using the sparsity promoting ensemble Kalman inversion. So the true system is still the standard Lorentz system plus some noise. And for the model system, we try to build the dynamics of the system by using all the first and second order polynomial basis functions. And for the unknowns here, it's just theta, the unknown parameters of the basis functions, and also the sigma, the diffusion coefficient of the noise term. And here I show the comparison of moments, which is the data we used for the two systems. One is learned from standard EKI, and one is learned from sparse EKI. As we can see, the comparison here is better by using sparse EKI in data space. And we also present the L1 norm of all redundant coefficients here. As we can see, sparse EKI is more effective to drive the L1 norm of all redundant coefficients to close to zero. We also try to compare the invariant measures of each state variable. And as expected, just because we have smaller L1 norm for all redundant coefficients, which means that all redundant coefficients are effectively driven to values close to zero. the extrapolation capability, the generalization capability of the model system by using sparsity KI is actually better than by using standard KI, where some redundant coefficients still holds non-zero value. So to summarize, many complex systems, such as Earth system, involve multi-scale dynamics, and there is usually no clear scale separation between resolved and unresolved scales, which justifies the use of stochastic closures. And we demonstrated the learning of stochastic closures based on time average statistics using ensemble Kalman inversion. And with the assumption that simpler explanation is often better, we imposed sparsity constraint into EKI and showed improved performance of learning stochastic closures. So for those who are interested in this work, there are some more details can be found at 2 archive paper as listed at the bottom. So with that, I'm happy to take any question. Thank you.